All right, next I want to kind of start taking some baby steps towards this more comprehensive wave theory that is going to be encompassed by what's called the Schrodinger equation. And we're not to the Schrodinger equation yet, but we're going to start talking about the waves that can make up a particle of matter and look at some of the properties of these waves. And one of the simplest ways to get started with this, and we're not doing the Schrodinger equation yet, but we're looking at some solutions to a fairly simple problem. Now simple, you might say, no, this is not very simple, but in comparison to the other problems we can look at, this is a simple problem. Okay, and so this is called the particle in a box. So for the particle in a box, you could imagine this to be analogous to, say, a tumbleweed in a ditch. Okay, so you would be at some low energy state here, and it would be hard for the tumbleweed to leave the potential energy barrier. But what we're going to do here for mathematical simplicity is to let the potential energy barrier go to infinity, so that we have a region in here where U is equal to 0 when X is less than L and greater than 0. And then, so this is X equals L. This is a one-dimensional particle in a box. We'll eventually be able to look at 3D particles in a box, but the advantage of looking at a problem like this, even though it only is approximately satisfied by real physical examples, is that the math is a lot easier to follow through with here. Okay, and so let's imagine then that we've got an electron that's bouncing back and forth inside of an infinite potential energy barrier. It means it can't get out, because it would need an infinite amount of energy to do it. So if the electron had a certain energy, E, that would just be equal to its kinetic energy, if it's non-relativistic, because the potential energy is 0 inside the box. E, in general, is equal to K plus U, but if U is 0, this is the only place where the electron can exist, then the total energy is just equal to the kinetic energy. It's going to bounce back and forth here. Let's assume elastic collision so that no energy is lost by the electron as it bounces back and forth. So it just keeps doing this, just keeps going back and forth. And that's what we'd expect as a particle. But what would we expect if we think of the electron as being a wave? Well, if we think about it as being a wave, then what we would expect are standing wave oscillations that could occur. And so these would occur for different values of the energy of the electron. But the energy of the electron is related to the momentum, right? Because the momentum is h over lambda. Okay, so here the electron has a wavelength, and that wavelength can set up a standing wave condition inside of the box. And so this is not that much different mathematically from a vibrating string problem. In a vibrating string problem, this would be your n equals 1 mode. That'd be your fundamental harmonic. Then you'd have n equals 2. That'd be your first overtone. You'd have n equals 3. Look like this, etc. And we're going to get the same thing with the electron wave. So in other words, we get an electron moving in one direction, then we have the reflecting electron moving in the other direction. And so those two waves can interfere and produce a standing wave pattern. So for n equals 1, if this is the length L of the box, then you can say here that lambda 1 is equal to 2L. For this one here, we've got lambda 2 is equal to L. Okay, so this then is basically our standing wave boundary condition is that we have nodes at the endpoints. Okay, and then for n equals 3, we're going to have 1/2, 1, 1.5 wavelengths equals L. Okay, so here we're going to have lambda 2 equals L. Here we have L equals 3/2 lambda 3, or lambda 3 equals 2L over 3. And if we were going to go to higher harmonics, then this would just correspond to different wavelengths that the electron can have. Okay, so how do these wavelengths relate to the speed? Well, the velocity of the electron times the mass is equal to h over lambda. Okay, so as the wavelength gets bigger, the speed goes down. So a larger wavelength then corresponds to a lower velocity. So as we get up to when we have the longest possible wavelength, that's going to be the slowest possible velocity that this electron can have bouncing back and forth. Okay? But then if we give it some energy and we decrease the wavelength by a factor of 2, that increases the frequency by a factor of 2. And that gives rise to a velocity that is faster. So if you can give it just enough energy, it goes from doing this to doing that, but nowhere in between. So in other words, you can't just give the electron a little tiny bit more energy and expect it to go just a little tiny bit faster. It can only go at speeds that correspond to those specific values for the wavelengths. Those are the standing wave patterns. And so what about all the other wavelengths that it could have? Well, they cancel out because of destructive interference, just like with a resonating string. You only have certain harmonics that can survive, and so the same thing is true here. These are the only harmonics that can survive. Now, if the length of the box were different, then this would kill off these electrons, but it would give other electrons a chance for life, ones that have different energies. And so this is the standing wave boundary condition then, and so this is basically the condition for constructive interference. Meaning that we're talking about standing waves. Just like, and it's really, I like this example a lot because it's just like what we did in physics 2AP with the vibrating string. It's the exact same math that goes along with this. And so what we could do then is generalize, and we can see that lambda n then is going to equal 2L over n. Okay, so that gets us lambda 1 is 2L over 1, lambda 2 is 2L over 2, lambda 3 is 2L over 3. So I could predict lambda 4 then would be 2L over 4 or L over 2. Okay, so lambda 4 then would be 1, 2, 3, 4. Right? So that means that the wavelength of the lambda is just going to be 1/2 a wavelength, or 1/2 of the length of the box. Okay, so this is our expression then for lambda. We know that we're dealing with sine wave harmonics, and we know that the total energy, E, is equal to kinetic energy plus potential energy. But because we're inside of an infinitely high box with no potential energy inside the box, this is just total energy of the nth harmonic equals the kinetic energy of the nth harmonic. So what is that? That's going to be Pn squared over 2m that P for the nth harmonic is equal to Planck's constant divided by the wavelength. And so then we can plug in that value for lambda n. That gives us h over 2l over n squared over 2m. Or En is equal to n squared h squared divided by 8ml squared. So this gives us a condition then on the allowed energies that correspond to these allowed values for the wavelength. So lambda n equals 2l over n gives us the allowed wavelengths that produce a standing wave pattern of the matter wave, and En is going to be equal to h squared over 8 ml squared times n squared. Okay, and so these are the allowed energies. Now, why are we interested in a problem like this that doesn't really have a physical analog? I mean, we do have finite square wave problems, and so this is somewhat equal to that if we make some approximations. But why are we interested in looking at this right now? The answer is, doesn't this remind you a lot of what we just did with hydrogen? With the electrons, they had a certain set of allowed wavelengths that could exist. For the hydrogen atom, it was 2 pi r equals n lambda. That was our standing wave condition for the hydrogen atom. And the nth state energy was minus 13.6 eV over n squared. So we've got that same sort of thing going here. And so that means that the math that we're working with here, although simpler than the math that we might try to solve using what we'll eventually look at as being the Schrodinger equation, gives us the same kind of solutions. And so it gives us an easier way of looking at the kind of solutions that we're going to be looking at later with the hydrogen atom, which has tougher math when we solve the Schrodinger equation. Okay, so with that idea in mind, that there is a good reason for doing this, let's find some energies. Let's find the energies. If the particle is an electron, m equals 9.1 times 10 to the minus 31 kilograms, and the length, let's say, is about an angstrom, 10 to the minus 10 meters. Okay, so we could do that then by noticing here that this is just a constant multiplied by n squared. And so let's find out what that constant is. En then is just going to be Planck's constant squared, 6.63 times 10 to the minus 34 joule seconds squared divided by 8 times the mass of the electron, 9.1 times 10 to the minus 31 kilograms times L squared, which is 10 to the minus 10 meters squared. And that's all times N squared. All right, so let's knock these numbers out. That gives me 6.03 times 10 to the minus 18 joules times N squared. And let's just do one more step here where we convert joules to EV. So En then is 37.7 EV times N squared. Now why did I use EV here rather than joules? Well, the answer is that the joules number is tiny, right? But here's a more natural set of units for the kind of problems that we're dealing with where an electron is confined to a distance that's comparable to the size of the hydrogen atom, to the Bohr radius. Okay. But here, it's a different problem, of course, but we're still trying to keep the scales of things under control. Okay, so now let's go and take a look at the screen. What we see then is that that's our E1 times N squared. Okay, so E1 then is going to be 37.7 EV on this, for this bottom minimum energy state. And corresponding to that, we have a psi1. That psi1 is going to be equal to this fundamental vibration, where lambda 1 equals 2L. Okay, and then don't worry yet about what the psi squared is. I'm going to get to that in a little while. Then the E2 would be 4 times E1, because it's N squared times E1. N cubed times E1, that'd be 3 squared is 9, or I'm sorry, 3 squared is 9 times E1, 4 squared is 16, 5 squared is 25. So if we look at these energy levels then, where this is 36.6, or 37.7, sorry. And this is 4E1, this is 9E1, and then we keep going up. The next one would be 16E1. Okay. Then let's say that you have an electron that's in this energy state. Then the electron is going to look like this. This is going to be our, we call our psi1, where psi is what we'll call the wave function for the electron. That's the first time that I've called it that, but we're going to get into that a lot more in a little while. And so then it's only going a certain speed then. Now we could figure out what that speed is by knowing that 2L is equal to lambda 1. P1 is equal to h over lambda 1. So that would be h over 2L, right? And so then we could say that V1, the velocity of that electron, is h over 2mL. Okay, so let's just do that for this one particular electron, just so that we have a good feeling for how this is how this would work with other states for the particle in a box. So lambda 1 then would be 2L. That would be 2 times 10 to the minus 10 meters. Be double the 1 angstrom width of this. And then P1 would be h over lambda 1, or h over 2L. And so V1 would be h over 2mL. So let's figure that out too. V1, 6.63 10 to the minus 34 divided by 2 times the mass of an electron times 10 to the minus 10 meters. So this will give us the velocity then of the electron in this ground state. Okay, so that's going to give us 3.64 times 10 to the 6 meters per second. So this is still not relativistic. This is just 1/100th the speed of light, roughly. But that would be the speed of the electron at that particular point. Now, how would this work then if we went up to a higher energy? Well, the energy, E, goes like P squared over 2m. And so if we went up to a higher energy, say 4E1, then that momentum, the wavelength would be cut in half, the momentum would be doubled, the momentum squared would be quadrupled, and so the velocity would be 4 times this value. Okay, and so you can work this through and just verify it for yourself with P2 and then solving for V2 the same way that I did here. What you'll find is that V2 is going to equal 4 times V1. Okay. And that means that the electron, as it bounces back and forth in this ground state, can't go at any other speed, but if it gets just this right amount of energy, it can start going that much faster. Okay. And so that much faster then, in this case, just corresponds to the next highest energy state for this system. Okay, and so you could do the same thing then with V3. V2 then would be equal to h over, well, in this case it would be L, mL. So sorry, that would be double the speed when it's in the second state. In the third state, V3 would be h divided by 2mL over 3. Okay, so the velocity is going up, but it wouldn't double the next time. We just go up by a factor of 1.5. So that's what would happen as we went to each one of these states, is that the electron would discontinuously jump to that next highest energy state and would suddenly start moving at a different speed and couldn't move at any other speeds that are in between, because those would cancel out by means of destructive interference. And so only the standing wave patterns are the ones that are described by this equation would be the ones that would hold. And in general, your momentum of the nth energy state of the photon will be h over lambda n, which would be h over 2L over n, or nh over 2L. Okay, so that would just be an integer multiple of our fundamental momentum, which would be mass times v1. All right, so if the electrons, say, were in this state and it then decided to decay back down to the ground state, it could do so by means of releasing a photon. So in other words, you could give it a photon to kick it up to this energy state, but you'd have to quadruple its energy in the process of giving it that photon. But then if the electron in this higher energy state wanted to drop back down to the ground state, then we'll have to give off that photon. Okay, so let's find the energy of that photon. And what I'm hoping that you'll see here is that this is really similar to what we're doing with the hydrogen atom. So delta E21 is equal to E2 minus E1. And so that's going to be 4 E1 minus E1 equals 3 E1. So that's the difference in energy between these two. That's delta E, 2,1. And that's going to equal HC over lambda 2,1. Because that difference in energy would have to be accounted for, in this case, by a photon being given up. Okay, so 3E1 then would equal HC over lambda 2,1, or lambda 2,1 would be HC divided by 3E1. Okay, now we don't want to confuse these wavelengths. We want to be very careful here. This is the wavelength of a photon and not the wavelength of the matter wave. Okay, so this is our photon wavelength. Whereas this wavelength that we're talking about here is the electron wavelength. Remember, they both have wave-like properties, and so we don't want to confuse them. This is another place where I've seen people make mistakes in the past, is getting the wavelength of the photon mixed up with the wavelength of the matter wave. It's understandable, but just watch out for that. So here, lambda 2,1, the wavelength of the photon, going from n equals 2 to n equals 1, is going to just be equal to 6.63 times 10 to the minus 34 joule seconds times c again, 3 times 10 to the 8 meters per second divided by 3 times 37.7 EV, and then again I'm going to convert to joules, 1.6 times 10 to the minus 19 joules per EV. And so that then is a way that I could calculate the wavelength of the photon, lambda 2,1, that's given off when the electron makes that transition. So that is 1.09 times 10 to the minus 6. Meters, or that would be 1090 nanometers, be an infrared photon. Okay, so you could certainly get higher energy photons that might even be in the visible part of the spectrum by going from higher transitions. Maybe 16E1 to E1 would be 15E1 instead of 3E1. That would give us 5 times more energy in 1/4 of the wavelength. So that would put this into the visible range. Okay, and so it's something that were to decay then from 16E1, or the 4th energy state down to the first one, would be a visible photon. Okay, so the rules then that we were using before with the Bohr atom for the hydrogen atom will also work for this particle in a box. Okay, and so that means that we perhaps can use this result, because we already know what the result should look like, as we now start to probe more deeply into the nature of the Schrodinger equation.